This is a recording video for section 7.2, solving exponential equations. This is actually the day 2 lesson where we are going to be doing application problems. So if you take a look in the box, you're going to see two different forms of an exponential equation. So the top one is generically the general form, y equals a times b to the x, where the base always is a number greater than 0, but not 1. And the other formula is for compound interest. And I'll talk about each of the formulas as I use them. So starting with the general form on the front side, A in that formula is always going to represent the initial amount of whatever it is you have. B, of course, is going to be the continuous rate of change, the base, and Y is the amount you have after X amount of time. So take a look below at problem 1. It says, Kristen starts an experiment with 7,500 bacteria cells. After 4 hours, there are 23,000 cells. So first off, I want you to understand we can think of that information as two ordered pairs. At the start of the experiment, Kristen has 7,500 bacteria cells. So at time 0, because X is the time, we have an amount of 7,500 cells. That implies the ordered pair 0, 7,500. After 4 hours, there are 23,000 cells. So at time 4 hours, we have 23,000 cells, where Y is the amount of cells we have, and X is the time for which we have that amount of cells. So if we go to our generic model here, y equals a times b to the x, I'm going to plug in for a the number of cells we have, which is 7,500 when we start the experiment. Y, of course, is 23,000, and that's the number of cells we have after 4 hours. So notice for the time, we plug in 4 for x, because that's the time that it took to get 23,000 cells. And then for time 0, we plug in the 7,500 for the initial number of cells we have. Of course, now we have an equation we can solve by dividing both sides by 7,500 in the next line. And that gives us 23,000 over 7,500 equals b to the fourth. And then, of course, we can take the fourth root of both sides. We want to use as an exact amount as possible, so we don't want to approximate by dividing 23,000 by 7,500 and rounding. We want to let our calculator do that, and then we can take the fourth root of that quotient, and that, of course, right here is about 1.323. The more digits you have, the more accurate your answer is going to be. I rounded to the thousandth place. I think that's a good place to round. And then for our final answer, which is the model, we can see right here, we want to put in 7,500 for the initial number of bacteria cells, the base 1.323, and then we leave X and Y unknown, so it's a generic model we can use to do part B. So part B then says how many bacteria cells can be expected in the sample after 12 hours. We're just using that model and substituting in for X 12, and I rounded it to the nearest bacteria since it's a very large number. And that's 215,665 bacteria. All right, so let's look at our second problem. It says in 2000, the population of Phoenix was 1,321,045. So this is our initial population for the year 2000. By 2007, 7 years later, it was estimated that the population was 1,512,986. Often for the years, we use just a digit. We don't use the actual year. So for the year 2000, I used 0 as my initial year. And then my number of people was the population. And then for my second ordered pair, the year is 7 because 7 years elapsed, and my population is the second number, the 1,512,986. The rest of what I do here is like number 1. I start with my generic model. I plug in for A, the initial population, and for Y, the population after 7 years, and then I plug in 7 for the time, which is X. I divide both sides by the initial population, and then I take the 7th root of both sides, and I get for B about 1.0196. So then my generic model, which you can see right here, is Y equals 1,321,045 times the base, 1.0196. I carried it out to the 10,000ths because of that 0, just for greater accuracy, and then raised to the X. And then in the second part, part B, I then use that equation to predict the population in the year 2013. Of course, I'm plugging in 13 for X, and you can see I got 1,700,221 people. I rounded to the nearest person. So that's the first type of model you'll be dealing with in your homework. Then the second model is compound interest, and you see that formula up here at the top. And on the back side, we're going to be dealing with that model. In that model, A is the amount you have in some account. It could be a bank account, it could be like a 401k account, an annuity, an IRA, anything that you're accumulating compound interest. So A is the amount you have in the account after T years. P, the principal amount, is the amount you start with and invest. R is the interest rate. We do need to express it as a decimal in the actual formula. And N is the number of times you compound that money per year. So let's go to the back side, and you're going to see this worked out. It says an investment account pays 4.2% annual interest compounded monthly. If $2,500 is invested in this account, what will be that balance after 15 years? So what we have to understand is the 4.2% is your interest rate. When we use it in the formula, we have to use it in its decimal form. So that would be 0.042. You just divide 4.2 by 100. That's what percent means. And that's the decimal 0.042. Compounded monthly, that is going to be the value of N, and monthly means 12 times a year. The initial amount is the 2,500. That's your principal. That's 2,500. And then they want us to find out the account balance after 15 years. So that's T equals 15. So then here's our formula. And notice how I plug in. I plug in for P with the 2,500. I plug in for R with the 0.042, for N, which gets plugged in twice in the formula, 12, and then T with the 15. At that point, I can simplify it step by step, like I took the 12 times 15 is 180. The 0.042 is divided by 12, and added to 1, and that's 1.0035. If it's not a terminating decimal, you might want to just type in the whole thing and let your calculator do the computation. You could actually do that up here as well. I didn't because it could simplify. Some calculators, you may need to use parentheses around the 12 times 15 because it might only raise it to the 12 and then multiply the result by 15. So you need to check your calculator out to see what works, but this is definitely the answer. So try it on your calculator and see, do you get $4,688.87? We always round to the nearest hundredth, the nearest cent. Each of these is a little different in what they give you, so I'll let you take a look at each of these. I do have the examples on Canvas as well, but take a look and make sure you are getting the same outcomes and are okay with using this formula. And then the one thing I wanted to say, sometimes they say bi-weekly as the number of times they compound. That can mean every other week, which if there are 52 weeks in a year, that could be 26. Or that can mean twice as many weeks. 52 times 2 is 104. Sorry, getting a drink. It's probably more common to think of bi-weekly as every other week and 26 times. So look at that in some of the homework problems. Monthly is 12 times a year. Compounding. Annually is once a year. Semi-annually is twice a year. Quarterly is 4 times a year. I think that is all of them. If we have problems, we'll take a look on Tuesday. Have a great day. Thanks.